Welcome back. How does the derivative f prime change when we make the transition from normal calculus 1, the real line, to the complex plane? Let's start with the real calculus definition. So over the real numbers, we define in any calculus 1 course the derivative to be the limit of this difference quotient, f of x plus h minus f of x over h, and that's the limit as h goes to 0. Another formula for the same thing is the limit as w approaches x of f of w minus f of x over w minus x. These definitions are not really different. It's just that we're using w for x plus h, and then of course w minus x is going to be h. Graphically, this represents a calculation of rise over run. So the denominator here, h, or in this notation, w minus x, is this distance here. This is h, which is w minus x. The numerator, f of x plus h minus f of x, or f of w minus f of x, is the difference between these two values. So this value here is f of w, this value here is f of x, and the distance between them, of course, is f of w minus f of x. So this is rise over run for these points, which tells us that this is a calculation of the slope of the line, and of course it's the line connecting these 2 points, which gives us this slope. Now, that's a secant line, of course, and when we take the limit, we have to imagine this point, w, moving towards this point x, and this secant line gets closer and closer to the tangent line, which is why we say the derivative is the slope of the tangent line. So this line is without regard to calculating the limit, and then when we calculate the limit, this line is, the slope of this line is going to be the derivative f prime. So slope is f prime of x. Now, our interest is in complex analysis. How does this change when we do complex analysis? Well, let's reveal the complex definition of the derivative here using the full power of the complex numbers. And you'll see it doesn't change one bit. So the only change is that since we usually use variable z to represent an arbitrary complex number, we write f prime of z. So f prime of z is going to be the limit as w approaches z of f of w minus f of z over w minus c. Now, this is exactly the same thing as this, and you could write this form as well. It doesn't make any difference. So this is good news. This means the complex derivative is exactly the same thing as the real derivative. That means that all of the calculations that you might remember from calculus 1, where you have to use the definition of the derivative to calculate the derivative of a function, they apply equally in the complex case for functions like f of z equals z squared, for example, so long as none of those proofs actually assumed that the real variable x you were working with at the time was actually a real variable. If there's no assumption that that variable was actually real in those proofs, then they will go through no problem. And we'll see some of those proofs later. This doesn't tell the whole story. It gives the impression that the complex derivative and the real derivative are exactly the same. They are in form, but let's look at the definition of the limit, and we'll see that there is a change to be concerned about here, after all. Here's the definition of a limit generically. The limit of f of z as z approaches z naught is the single value L, such that for all epsilon there exists a delta. For all z, if z minus z naught is less than delta, then f of z minus L is less than epsilon. In practical language, what this really says is no matter how close you want f of z to get to L, that proximity is measured by epsilon. So long as z is close enough to z naught, that proximity is measured by delta. There is some proximity so that if z is that close to z naught, then indeed f of z will be as close as required to L. So we will get f of z within the proximity epsilon from L, so long as z and z naught are no farther than delta apart. Now, this is the definition of the limit in the real case, and this is also the definition of the limit in the complex case, but there's something to be concerned about here. In the real case, this is absolute value here and here to measure the distance in the real case. In the complex case, of course, this is not absolute value but modulus, which is the correct generalization of the absolute value. So this is the definition of the limit, which is really implicitly meant here. And so we can open up the definition of the derivative to include the limit exactly. And what that means is that the derivative f prime of z is the single value L, such that for every positive epsilon, there exists a positive delta, such that for all, now I need to say W, for all W, if z minus W is less than delta, then now I'm not taking the limit of f of z, I'm taking the limit of f of W minus f of z over W minus z. So I'll place that in here. So then f of W minus f of z over W minus z minus that magic value L, which is going to be the derivative f prime of z, is less than epsilon. So here I'm just applying the definition of the limit directly to write out what it means to take the limit of this function as W approaches z. Notice that the z here is playing the role of the z naught, and the W is playing the role of the z. So to be perfectly consistent with the way I wrote this, I should probably write W minus z here. Although, of course, it's modulus, so it doesn't make any difference. Now, this is the correct interpretation of the derivative in the real case, although it's strange to use a variable z for a real variable. It's also the correct notation for the derivative in the complex case, but as I noted before, this absolute value needs to be interpreted as modulus if we're dealing with complex numbers. But there is actually a real difference here, and one that has some significance, and that is this for all W. Now, the for all W in the limit refers to every possible value that W could take. It's not really for all W, because we immediately say, if this distance is less than delta, then this condition. So really, this for all W taken together with this precondition means for all the W's that are within a distance of delta from the noted value z here. But that still is a different condition over the complex numbers compared to the real numbers. If this were the real derivative, then this would implicitly be for all W in the set of real numbers. And this condition here, that W minus z in absolute value is less than delta, would be the condition that z is lying on the real line, and we have a distance of delta, either direction, and W is somewhere in that range. However, if this is the definition of the derivative in the complex case, then this for all W is not for all real W, but for all complex W. And then, again, not really for all, but for all within this range. But that is now different. Even if z is a real number, it's a real number living on the complex plane somewhere, and the w's that are within the distance of delta from z lie in the complex ball, centered at z, with a radius of delta. So the w's here that matter will be anywhere within that ball. Well, who cares? Well, by broadening this range of values of w in the quantifier for all w, and then broadening this, what we've done is we've required this condition for far more w than before. All of the w in this two-dimensional set instead of the w's in this one-dimensional interval. That means that for this derivative to exist and equal L, this condition must be true a lot more broadly for many more w than would be required in the real case. And that means that for the derivative of a complex function to exist is actually a much bigger deal than for the derivative of a real value function to exist, because this limit is a stronger condition on many more w's here. What does this mean for us in practical terms? Well, because we have essentially exactly the same definition of the derivative, in practical terms we can compute derivatives the same way, and we'll get the same answers for many derivatives in many basic cases. But because the derivative is actually, the existence of the derivative is a stronger condition on the function, what we'll see is that it's generally harder to demonstrate that a function has a derivative if it's an unusual function, like a piecewise defined function, for example. It's also it's also a logically stronger condition that the function has the derivative. And we'll see surprising theorems that say if a function merely has a derivative at every point in some domain, then something really strong happens, something interesting happens as a consequence of that. We'll see theorems of this form that don't have analogous statements in the real case because they're not true in the real case. So as a general rule, when you look at differentiability of complex functions, the analogy with the real functions gives you the impression that it's a simple condition on the functions that doesn't have a lot of substance to it. But as we dive deep into how we compute these derivatives and what are the consequences of having a derivative, what we'll see is, on the contrary, if a function is differentiable in a complex sense, then we will have a lot of powerful conclusions that we can make about that function. And that will be a more powerful and richer condition than you might anticipate. So we should look for that in the upcoming videos.